One application of studying circular motion is applying it to derive Newton's law of universal gravitation. And so to do that, what Newton was looking at was the motion of the moon around the Earth. And what he did, he assumed that that the moon follows a circular orbit around the Earth. In fact, orbits are a little elliptical, but it's close enough for approximations. And given that, you could figure out, well, what's the centripetal force? Because that centripetal force would be the force of the Earth pulling the moon, or the force of gravity of Earth on the moon. So using what we've learned from circular motion, we can get the relationships out of this. And so we know the period of the moon is 27.3 days, which is 2.36 times 10 to the 6 seconds. And then we know the distance to the moon, which is 3.8 times 10 to the 8th meters. And that's about 60 times the radius of the Earth. The radius of the Earth being, this from the center to the edge, that's the radius of the Earth. So it's about 60 times that distance to get out to the moon. How do we know this distance? How did Newton know this distance? Well, they use it's parallax. It's called parallax. You measure at the same time, or not the same time. You measure the angle that the moon sweeps out, and then you can, using trig, you can figure out how far away it is from two different locations. All right, anyway, back to what we were doing. So what we want to do is use circular motion. So we'll determine the centripetal acceleration of the moon. And the centripetal acceleration would be instead of using velocity, we need to use period. So it's going to be 4 pi r y squared times r over t squared. Make sure that's right, the t squared, yeah. So then we can just substitute everything in. I'm not going to do that, but you plug in all these numbers, and you get a centripetal acceleration of 2.69 times 10 to the negative 3 meters per second squared. All right, and then we don't know the mass of the moon, but what we can do is we can think about ratios. And so what he did is he actually said, okay, well, what if we take the moon and we shrink it down into just a point? And so we have this moon point, same mass, but it's just a point. And we bring it down near the Earth's surface. So we're actually on the Earth. Then the acceleration, if we just release it, so in other words, it's not in an orbit anymore. We just pull it down, we have something of the same mass, and we release it. Then we know the acceleration here on Earth of the moon would be g. That's the 9.8 meters per second squared. So now we can look at the relationships of the force, because we know that this is a force of gravity here, and then we know this is also a force of gravity. And so what we want to look at is, what's the force of gravity? You know what, I'm going to use big G. The force of gravity way out here at big R, so we'll say at big R, over the force of gravity over here at the radius of the Earth. So on Earth, I'll just put on Earth. So way out here, we know that it's going to be the mass of the moon times the centripetal acceleration. That's Newton's second law, mass times acceleration. Down on the bottom, we get the mass of the moon times g. And you can see that the mass of the moon then cancels out. So we get the ratio of the forces is going to be the ratio of the accelerations. 2.69 times 10 to the negative 3 divided by 9.8, which is approximately, it's very close to, 1 over 3600, which happens to be equal to 1 over 60 squared. And that 60 is right here. So at 60 times the radius, we have this ratio. And so what you could deduce from that is that the gravitational force is proportional to 1 over r squared. And that's the first thing that you'll be testing here in a little bit. So the gravitational force is proportional or indirectly proportional to the square of the radius. Okay, the next thing he did is said, well, what about the mass? Because we know down on Earth, if I have a more massive object, I have a greater force, so does it hold out here? and it does. So what he was thinking is, the force of gravity here on Earth, we learned, is m times g. And so the force out at the distance, the big G, is going to be the mass times like the centripetal acceleration. And so we can say that, number two, the gravitational force is also proportional to the mass of the object. We'll call it mass 1, or the mass of the moon, I guess you could call it, the mass of the moon. Now, for the next one, for the third thing, it's just Newton's third law. You have the Earth, which is pulling on the moon. We've learned this. Well, the moon also pulls on the Earth. So we could flip all this around, and through the same logic, we could say that the force of gravity is also proportional to the mass of the Earth. And these three things are all true. And now we can put them all together. And we could say that the force of gravity is proportional to, since it's proportional to both masses, we just multiply those, mass of the Earth times mass of the moon over r squared. And then if you remember, to go from proportionality to an equation, force of gravity equals some constant, I'm going to call it big G, and that would be mass, we're going to just say mass 1 and mass 2. So these are two objects over r, the distance between them. And this is Newton's law of universal gravitation. Now what you're going to be doing is you're going to be determining big G. So you're actually going to do, you're going to verify these, and then you're going to figure out what big G is. So again, you're going to verify the force of gravity is proportional to 1 over r squared, and it's proportional to the masses. And then you're going to use all of that data to figure out what that value of G is. And you're going to do that using a PhET sim. This one. Let me reset it. So what you're going to do with this thing is build an Excel sheet, something like this, where you have the radius, the masses, and the force. And then you're going to plot it and then do your regression. So what you'll want to do is, for the first one, you're going to test R, so you'll leave the two masses alone. You can move this over and you can slide this up so that you can fix the R value, or you can change it. So maybe at like here, so at 2 meters, and then there's your force. And notice that the forces are the same, they're just in opposite directions. So you would record the radius, the two masses, and the force, just one of them since they're the same. Then you change the radius, record, change it, record, and so on. So you can figure out what's the relationship when you plot it all, what does it look like. So that's for the radius. And then what you'll do for the mass is you'll hold the radius constant, and then you just start changing one of the masses and record the force. Plot that, and then put it all together and determine what G is. So again, what you'll be doing is you'll verify, let me see purple, you're going to verify that force is proportional to 1 over r squared and proportional to the mass, and then determine G. And that'll be your assignment, your homework assignment.